about the impurity problem, so the theory point of view of this problem, why it is interesting, and I would present results for S-wave resonances, and in particular the extension of the previous work to narrow threshold resonances, as it was needed for to explain the experiment in Innsbruck. And then I will continue to describe what happens if you, instead of an S-wave, you have a P-wave resonance between the impurity and the surrounding Fermi gas. Okay, so this work, I am at the Institute of Photonic Sciences in Barcelona. I work in a group of machine learners. Okay, so let's start. So this is the outline of my talk. I will be speaking of the theoretical problem of one impurity. So here it's a single particle immersed in a large Fermi gas, which is considered to be ideal. So there are no interactions between they are identical fermions, so they do not interact with low energies. And I will confine myself to t equals 0. And so I will describe first this S-wave part, which is work that's been done in collaboration, as I said, with the Felix team, so the group of Rudi Grimm and Florian Schreck and Matteo and the co-workers, and with the theory help of Georg Brum. And while the P-wave part has been done in collaboration with Jesper Levinsen, Frederick Chevy, and Carlos Lobo. Okay. So, brief slide of motivation, why this problem is interesting. So understanding the properties of a single impurity or a few impurities, as long as they are very dilute, they don't see each other basically. In a Fermi gas provides important insights in the phase diagram of imbalanced Fermi gases. It gives important information about the coherence properties and the decay mechanism of the fundamental quasi-particles constituting an imbalanced Fermi gas. It gives insights as well on the possibilities or impossibility of reaching itinerant ferromagnetism, and which is an open problem since many years, since the original proposal of Stoner in the 70s. So the itinerant ferromagnetism is exactly that, in presence of strong repulsive interaction, the transition between a mixed state in which few impurities just displaced in the gas, and towards a region in which the impurities, the one component separates, and in the two components spatially separate in different regions of the medium. And regarding the P-wave case, P-wave superfluids in particular have a lot of interesting properties that are not present in S-wave superfluids. P-wave superfluids can be polar or chiral, and in G dimension they can even have topological properties. And so it would be very interesting to realize these P-wave superfluids, but they are very challenging for various reasons. And so an analysis of the impurity problem may help us to understand better these systems. Okay, so I mentioned before that we want to understand the coherence properties and the decay mechanism of these quasi-particles. What are the quasi-particles? We are dealing with a many-body system, which is a complicated system. That's a nice definition often of a many-body system, in which we don't know exactly. I mean, particles are behaving, colliding between each other, and in a very complicated way. And we want to analyze the system in a simpler term. So what Landau came out about many years ago was why should we care about real particles? What important in this system are the excitation, and those behave as quasi-particles. So what's a quasi-particle? Something much more simple, that it moves straight in a line, basically has very limited interactions within each other, and but of course they cannot be exactly the same particles as before. So quasi-particles, just before coming to the properties, there is another very illuminating image from a book called Matuk that says, okay, if a real particle is a real horse running in an empty field, a quasi-particle is like a horse running in the desert. So it will be, by running in the desert, we get surrounded by a big cloud of sand, and it will, its properties will be modified by the presence of the desert. But still, it's still a quasi-horse, I mean. So. Okay, so what's a quasi-particle? A quasi-particle is a free particle. It's in the sense that it moves its motion is described in very simple terms. That has, let's say, the same quantum numbers as the original particle, but has a renormalized mass that in this case would be, I mean, the force is dragging around the sand, so it has to bring around some more weight. And it has a chemical potential, in this case would be the binding energy between the force and the surrounding cloud. And the force is basically blind, so it has troubles to see other quasi-forces. So there is strong shielded interactions between the quasi-particle. And also there is lifetime, in the sense that one quasi-particle can transform itself in another quasi-particle, and this will take a certain time, which can be estimated by looking at properties of these quasi-particles. Okay. So the impurity problem in this case, as Matteo already mentioned, will have some overlap with this talk in some sense. Of course, it's if we start with a few impurities in a Fermi gas, and these are non-interacting, the two gases don't mix and they don't see each other. If we turn on interactions, we can either turn on repulsive interaction. In this case, the impurities repel the surrounding Fermi gas, and therefore the density around the impurity is slightly reduced. In the opposite case of attractive interaction, the particle is the red particle in this case are attracting the blue ones, and therefore the density is increased, and these are, let's say, attractive. This will be termed attractive polarons. And if the attraction becomes extremely strong between the red and the blues, what can happen is the formation of molecules. And these molecules themselves, so this is a bound state that appears in the system, and these molecules themselves interact with the gas and modify the surrounding gas. So also the molecules will be dressed molecules in this case. Okay, so this was in the context of Fermi gases, this system, at least the attractive polarons and the transition to molecules was addressed first in this paper by the MIT group a couple of years ago. Okay, so let's start with S-wave resonances. So in order to look at this problem, one can start with a two-channel model. So we want to look at the interaction between the blue and the red particles. So the blue is, the red particles form a Fermi sea, which will be indicated by Fs. So this is the initial state in absence of interactions. And the blue particle, it's created with momentum 0. So this operator creates a particle in the Fermi sea, a blue particle in the Fermi sea. And the Hamiltonian for the system, it contains a free kinetic energy for the red and for the blue. It contains a term that describes the formation of molecules eventually. So B is a bosonic operator for red and blue, which therefore has mass 2m and eventually binding energy epsilon. And then we have a contact interaction, which transforms two particles, a spin up and a spin down, into a molecule, and vice versa, destroys the molecules and forms two particles. And so the simplest ansatz to proceed, and which can be plugged in this Hamiltonian to describe the system, it's in the terms of an expansion in particle holdings. So the initial state, which is this one here, it's renormalized by a factor square root of z smaller than 1, and we add to the wave function terms which contain the creation of two. So sorry, this I think I mixed up the notation. So this should be the creation of the creation and destruction of one red particle, and the blue particle must acquire the difference in momentum. So this is a particle. These two are a particle and a hole in the Fermi sea. And the blue particle acquires the difference in momentum. And this is called, it's been introduced by Chevy some years ago, and since then it's been called Chevy ansatz, and it's been used also in many other works. And okay, so if one plugs in this ansatz in the equation, as also Matteo was mentioning, one gets 3 branches of excitation. There is the attractive branch of excitation, which goes down here. There is a molecular branch, that is this one here, which actually shows up as a continuum because the molecule can be formed with any particle from the Fermi sea with momentum between 0 and kf. And there is also a red branch of excitation, which is this one here, which arises at positive energies. And this is the branch regarding the repulsive polarons. Okay, so the repulsive polaron represent somehow a new quantum toy in the sense that it's provide us with the gas with strong repulsive interaction in the sense that this branch goes up in the strongly interacting regime. Nonetheless, there is the presence of two well-defined excitations below the polaron, the attractive polaron and the molecule whole continuum, and therefore this red branch is intrinsically metastable due to the existence exactly of this weakly bound lower lying state. Okay, so this is the theory. Let's say this was the this was known. So let's play. We started discussing with them, and Matteo came up to me with this data some more than a year ago, and we started looking at numbers and things. And what came immediately to the attention was the fact that in the problem there is a range. One can define a so-called effective range, and this is of order the inverse Fermi momentum. And therefore, this brings about strong finite range effects in the problem. So this will mean that if this number is large, or comparable to 1 at least, it means that the physics in play depends on two parameters, not only KFA, as usually for broad Feshbach resonance, but also KF R star. And this will basically model the width of the resonance. Small KF R star means broad resonance, and large KF R stars mean narrow resonance. So what's a narrow Feshbach resonance? It's you may be familiar with the scattering amplitude in S wave. This is contains minus the inverse of 1 over A plus IK, and then in general contains quadratic and quartic and further terms in the energy. So K is the relative momentum between the two particles. And for a broad resonance, this term is negligible, and therefore the scattering amplitude is just 1 over A plus IK inverse. Close to resonance, this parameter R star can be related, written in this form. It's proportional to 1 over A background times delta V delta mu. So you can see immediately when the width of the Feshbach resonance in general in magnetic field is small, this will yield a narrow Feshbach resonance. Or at least when this product, when this factor is large, this will yield a narrow Feshbach resonance. What changes with respect to a broad Feshbach resonance? The molecular energy can be written in the usual form, 1 over A squared, proportion to 1. But A now is replaced by a quantity that contains the scattering length and the range. This quantity for when the scattering length is much larger than the effective range, this A star behaves as A. So close to the resonance, the black line here would be the bound state for a broad resonance, and the red line is the bound state that one gets for a narrow resonance. So for A much larger than the range, the resonance is still, the bound state behaves quadratically close here, but away from the resonance, the bound state becomes linear because A star becomes proportional to the square root of A. And so the bound state in a narrow resonance is actually much higher than in a broad resonance. Okay, so in general, Feshbach resonance can be termed as broad, depending on, in a two-body context, the range is much smaller than the van der Waals range. Or in a many-body context, when the KF, so the inverse distance between particles, times R is much smaller than 1. And it turns out that most heteronuclear Feshbach resonances are actually narrow. So the extension of the previous theories to narrow resonances would be is important to understand the heteronuclear Feshbach resonances in general. Okay, how to go on with narrow Feshbach resonances? The trick is to write the T matrix, at least in this formalism. One writes the T matrix, which describes the forward scattering of particles in the open channel, as a term that contains only scattering in the open channel, with terms that present a scattering in the open channel, then a coupling to a molecule, which is the blue line here, so a closed channel molecule, and then the particles are allowed to go out again in the open channel. And the molecule itself has a self-energy that depicts basically a molecule, the opening up into propagating in the open channel for some time, eventually having some scattering in the open channel, and then closing again into the closed channel. Long story short, it's very nice that if one works at formalism, one can just replace, to include the effects of a narrow Feshbach resonance, one can just replace the usual form for the scattering length, at least in this T-matrix formalism, into a scattering length that explicitly depends on the energy. And so the inclusion of the energy in this term yields basically the correct coefficient of k squared in the scattering amplitude. Okay, so this is depicted here. So if one plugs in this scattering length in the T-matrix for the problem, one obtains a low energy, exactly this term here with the correct coefficient. So if one plugs the full T-matrix in the problem and looks at the energies of the various excitations, so the x is the axis controlling the width of the resonance. So this 0 means broad resonance, and very large x means narrow resonance. So for a broad resonance, one has the ground state at resonance, and for equal masses is a polaron. This was well known with energy minus 0.6 EF, while the molecule is an excited state. It's actually even at higher energy, at positive energy. And when one considers increasingly narrow resonances, what happens is that the polaron energy goes up, while the molecular energy comes down quite rapidly. And at KF R star of order 1, one finds the two levels actually cross sharply. And for resonances which are narrower than this value, the molecule is actually the ground state at resonance. And for very narrow resonances, there appears also the repulsive polaron becomes a well-defined excitation, like even at resonance. What is interesting is that a narrow resonance actually corresponds to a weak coupling in the Hamiltonian that I showed you at the beginning. So the coupling G becomes small because G squared is inversely proportional to R star, basically. And so in the limit of large R star, the theory becomes perturbative, and only the first terms in the T matrix are important. And for example, in this limit here, one can work out analytically the energy of the molecule, which is the dashed line here, while the black line is numeric. So the theory becomes perturbative in the limit of large KF R star. So this slide here shows the polar molecule crossing at a narrow Feshbach resonance. So I show 3 lines describing various mass ratios. So the blue line is equal masses, while the violet and the pink describe respectively the case of one. I think I mixed them up. So this is the case of one impurity of lithium, of potassium. So a heavy impurity, equal masses, and a light impurity. And so what one sees is that as the resonance becomes increasingly narrow, the crossing point between the polaron and the molecule shifts progressively from the BEC side towards resonance, and then it goes progressively, increasingly to the BCS side. The dot here is the experimental value found by Innsbruck, and indeed what they found was that the crossing was on the BCS side. This was very puzzling at the beginning because we were expecting this crossing to be on the left side, on the BC side, for a broad resonance, which was this point here. The insert shows the energy of the two excitations at the crossing, and the tiny blue squares here indicates that in the limit of narrow resonances, everything again becomes perturbative and the critical interaction becomes proportional to KF R star, and the energy of the crossing to the inverse of this one. So these slides, you have already seen them, a big part. So this is are the RF spectra at low power that Matteo showed before, which evidence the repulsive branch of excitation and the attractive branch of excitation, which disappears at the crossing here between the green and the dashed line, which is the polar molecule crossing for this problem. And there is a molecule-hole continuum in the middle, which is visible only if one goes to high-power radio frequency spectroscopy, and this is shown here in the bottom part. And again, this plot has been also shown by Matteo. So these are the blue and the red curve describe the two-body and three-body processes that lead to the decay. And we expect that they sum up additively. This is a log scale, so the sum is basically equal to the maximum of the two curves. And the data align very well with basically the maximum of the two processes. What is, okay, I will probably skip this. This was also shown by Matteo anyway, so the details are in this paper that has been submitted in December and accepted recently. And also in a theory paper that I published recently as well. I will pass now to the second topic, so the P-wave resonances. How much time do I have?
10 minutes for talking.
So I will switch now to the second topic of that is P-wave resonances. Again, I will still be at t equals 0. So this is work I did in collaboration with Jesper Levinson and Shadi and Carlos Lobo. And so the problem is again the same. So we have one impurity in a large Fermi gas, and now we're imagining to tune the magnetic field such that we are close to a Feshbach resonance in P-wave between the impurity and the Fermi gas. And so what changes in the problem is that the P-wave scattering amplitude now has a different form. In particular, has a quadratic k-square term in the numerator. And in the denominator, the scattering amplitude, or the scattering length that we have in S-wave is replaced by a scattering volume. The range is that we had before, the parameter R star, is replaced here by a K naught, which is an effective range and has units of momentum. And the IK term that we had in S-wave is replaced by an IK cube term. The interesting thing of the P-wave resonance is that is usually a P-wave resonance is split into a doublet of resonances. And this was shown in a paper by 2004 by Chris Dickner and collaborator, David Jin and John Bourne, in which showed that a molecule, this was also shown yesterday by Martin Svirline, that if we have a magnetic field that is aligning the dipoles of the dipoles of the two electrons in the molecule, the magnetic field, and if we consider a molecule with a projection of the angular momentum with respect to the magnetic field axis of m equal plus or minus 1, the molecule is basically rotating in the plane with the two dipoles aligned orthogonal to the plane. And so the dipole-dipole interaction is between these two is repulsive. And while if we consider a molecule that's in the m equals 0 state, this molecule is rotating in this plane here. And therefore the interaction between the two electrons is repulsive, attractive, and in average the energy of this molecule here is lower than the energy of this molecule here. So we expect that in presence of a magnetic field, we will have a splitting between the molecule with plus minus 1 with ion energy larger than the molecule with m equals 0. And on the theory side, the analysis of the problem is very similar. We have again the same two-channel Hamiltonian, except with the same interaction term, except that the coupling now is proportional to P mu, so to the projection of P. So it will contain basically a cos theta term, and the interaction needs to have a cutoff. And the difference with the S-wave, this cutoff cannot be brought to infinity. So a P-wave resonance needs to be always considered as narrow. It has always a finite range, which has to be taken of order the van der Waals length. Else the theory is not renormalizable correctly. So upon proper renormalization, the theory depends on the scattering volume, V mu, and on the ineffective range K naught, which has to be taken of order 1 over van der Waals range. For the rest, the diagrams are completely the same as in the S-wave case. So the dressed molecule composed of a bare molecule plus bare molecule forming opening up in the open channel, propagating as two atoms in the open channel, and then this is the Lippmann-Schwinger equation for the molecule. The T matrix describes two particles in the open channel forming a dressed molecule and going out again in the open channel. And the self-energy is again exactly the same as in the S-wave problem. We have an impurity, which is now the spin down here, propagating, forming a molecule by interacting with a hole in the Fermi sea, propagating as a dress molecule, and then going out again as a spin down. Plugging in all the machinery into the Hamiltonian and working out the calculations, one can first start by looking at, let's say, the zero splitting between these two states, and then what one gets is a figure that looks very much similar to the S-wave case. So this is a spectral function of a single impurity that presents an attractive branch, a molecule hole continuum, and a repulsive branch. And the dashed line here is the energy of the molecule. But if we start to include, so I was pretty disappointed after the month's calculation and when this image came out, because it was like very similar to the S-wave case. But if we start to put finite splitting between delta, then things become more interesting. And in particular, when the splitting between the two resonances, so the energy, so if you want, the blue line here is the dressed molecule of this kind, and the red line here is the dressed molecule of this kind. So when the splitting in energy between the two molecules is sufficiently large, one observes the appearance of a third branch of excitations in the middle. So we still have an attractive branch, there is an intermediate branch here, and there is a repulsive branch on this side. What one can see also is that, so there is one molecule of this kind, while we have two molecules of this kind, because we have m equal +1 and m equal -1. So if one looks carefully, one can see that the color here is proportional to the intensity of the signal. So the color here, this is twice as white as this one here. So one has twice more amplitude of signal on this. So one can see that there is two molecules contributing to this part, and only one molecule contributing to the signal. So the residue of the +-1 molecule is twice as the residue of this 0. Okay, and one can work out again the quasi-particle properties much in the same way as for the S-wave case. One can calculate the energy, and that's basically what's done here. One can calculate the decay rate. One can calculate the residues of these quasi-particles. And what is interesting is, turned out to be very interesting, is the effective mass of these quasi-particles. So what's the effective mass is basically at low momenta is the coefficient that we have to replace the mass by the effective mass in order to reproduce the complete excitation spectrum of our particle at low momentum. And so we plot here the inverse effective mass, because what happens generally is that the effective mass in the low in this weakly interacting regime approaches the normal mass of the particle. So this would be 1. But as we approach a resonance, usually the particle gets heavier and heavier, the effective mass grows, and at some point the effective mass diverges and goes negative. And we have some situation in which the effective masses have opposite signs. So these are the effective masses of the polar, not of the molecule. There is some situation in which the effective masses, we can have, okay, sorry, and I missed that we have one effective mass for motion in the direction of the magnetic field, and one effective mass for the direction in the plane perpendicular to the magnetic field. So that's the blue curve is the effective mass perpendicular to the magnetic field, and the dashed line is the one parallel to the magnetic field. And these two can have different signs, what happens here. And in particular, they can even be larger. So the effective mass can even be, the inverse effective mass can be larger than the bare mass. So this means that the effective mass of the particle can be smaller than the bare mass. This was something that was not happening in the S-wave case. And this can be, we were very surprised at the beginning and it took us a while, but I think, so there is a general theorem saying that this cannot happen for the ground state of, for an excitation which is the ground state of the system. But this is not the ground state of the system, because this is depicting the effective mass of particles that are up here, and there are clearly excitations below it. And this result can actually be worked out analytically by looking at the first diagrams in the system, and one finds that the effective mass indeed is 1 plus V, where V is the scattering volume, and the scattering volume is negative on this side. sorry, positive on this side, and this gives larger inverse effective ones. Okay, and with this, I'd like to conclude. Thank you for your attention.
So we have plenty of time for some questions. It's interesting.
When you were showing the energy of the repulsive polaron as a function of the effective range, so KFR star, at resonance, you cannot go to very small values of R star. So you have to stop at some point. No, but why? So I mean for the repulsive, yes. Why you have to stop is because of the lifetime.
The lifetime, I didn't plot it, but there is a lifetime associated to it, which grows. It's very small here, much smaller than E, but grows quite abruptly.
Okay.
Therefore, there is no repulsive polaron for broad resonance.
Okay, I see. But then, so even I mean, for the smallest value of R star that you can reach, the energy of the repulsive polaron is half of the Fermi energy. So epsilon F is Fermi energy. Okay, yes. So yeah. So then it means that you never cross the Fermi energy, and so in a sense, going back to the results.
I don't remember exactly where did I stop it.
Ah,
so,
okay.
Anyway, so for the broad case, equal masses, what we found was a value of interaction strength for which the repulsive polaron was growing above the EF that was a bit larger than what you had. So we're finding you had about KFA equals 0.9. We found KFA about 2 point something. So in that case, the imaginary part given by this approach was still smaller than the real part. So that was giving somehow a transition, a well-defined transition.
I just want to give a comment for your criterion about for disturbing the narrow fashionable resonance. In your criterion, you require that the R star parameter to be much smaller than the van der Waals length for broad fashionable resonance. But as far as I know, for two particles interacting with van der Waals interaction, yeah, the first criterion. That's right. For two particles with van der Waals interactions, actually, in case of broad fashionable resonance where it's open channel dominant, the R star parameter is fairly comparable with the van der Waals length. So it might be better if you use small or equal. Yeah.
Okay, maybe you mentioned this, but well, I was just wondering whether this polaron is fermionic or bosonic. Okay, but it's
So the particle generally maintain the quantum numbers of the original particle. So the polaron in the weak coupling becomes the attractive polaron becomes a free particle. It has a zero energy in this scale, so it becomes a free particle. Therefore, the attractive polaron and the repulsive polaron are both fermionic quasi-particles. While the molecule asymptotically becomes a deeply bound molecule, which is a well-defined boson. So the dressed molecule is a bosonic quasi-particle.
because it's, I'm asking because if polaron, well, okay, if this fermion is dressed by only even number of fermion, then it should have odd number of fermion. Then
So the number of fermions is actually not an integer. In the dressing cloud,
okay.
The number of fermions is not well defined, and they are kind of weakly bound to the polar.
I see.
I don't, you can define the number of fermions or particles in the dressing cloud, and that's usually a number between +1 and -1, as Martin also was saying yesterday.
Okay.
But that's not changing the statistics of the.
Okay, still you can define this quasi-particle operator, which is fermionic. You mean?
Yes. So I think yes, that's my understanding.
Okay, thank you. Thank you.
Statistics is not changed by the dressing.
Okay.
One thing, in the calculation of the spectral function, you showed the self-energy that you have used. There was a slide. It was not clear to me if that self-energy, if you take this to the broad resonance limit, would be just a plain T matrix, or it is better in the sense that it includes those corrections that in the strong coupling limit will give you the correct Bose-Fermi, the correct, dimer fermion scattering length. Yes, that, okay. Sure. Sure. Yes, no, but as far as the polar molecule crossing, I agree with you. I have understood it, that you do better than plain T matrix. But for the spectral wave function, for the self-energy that you use for the calculation of the spectral wave function, it was not clear to me that what you're using, if you would take it to the broad resonance limit, would be better than the plain T matrix. I simply have not understood it. I'm just asking.
So the spectral function I showed is the ones for the polaron, for the single particle. So I think the color picture is this, and that comes out from. So if you use a so this one, yes. So if you use a but this is the experimental result. But if you use a T matrix for a broad resonance, what you find is basically lines. This line would all be shifted down, would be more deep, and this one would go up faster.
So you didn't calculate the spectral wave function. You simply calculate the
energies.
The energies.
But okay, so I calculated.
Okay. So sorry, I missed this point.
But this is the spectral function, the one for the P wave case. So I didn't show the one for the S wave because there was the experimental.
So just one comment on IP. I think it's an important question, but in the case of one single polaron, it's not so important statistic. But if you start adding more and you see how they interact, then this issue will be important of the question he asked about the statistics, what it is actually, and how many fermions are actually surrounding this guy. Just a comment on that. Now, the question I have is regarding your effective masses. Could you just bring that up a little bit? Yeah. So you mentioned that you getting these things could be negative, right, at the end. I mean, could you elaborate a little bit on that? I mean, what's the physical interpretation? Could be hinting that you have your approximations is breaking down instead of...
The particles are not the ground state anymore. So the ground state, basically this is a general property also for the S-wave case. The effective mass diverges and becomes negative in a region where the polaron is no longer the ground state. So if you come from here, the polaron is the ground state, and then its mass increases and it diverges somewhere here where the molecule, the red line, is already the ground state. So it's kind of telling you it's signaling that an instability has already been achieved. Yes. So in some sense, it's a negative mass, but for an excited state, which is not probably not the state. The same thing.